Okay, so to continue 11.2, when we have an initial point and a terminal point, we can find the vector between them. But also, if we have either an initial or a terminal point and we have the vector, of course, we can find what the other point was. So if you're given vector v is 4i minus 5k, write the vector in component form. Find the terminal point of the vector given the initial point, negative 2, 3, 5. Okay, so what do they mean by that? Write it in component form. Component form is that three numbers separated by commas. Now notice you see an I and a K and you don't see J. That's because J is 0. So this is the vector in component form. There's 0J. Find the terminal point given the initial point. So if we have the initial point, we know that normally terminal minus initial equals your vector. So using some algebra, that means your terminal point is equal to your initial point plus the vector's components. Which means all I should have to do is do negative 2 plus 4 for the x value, 3 plus 0, and 5 plus negative 5 to get 2, 3, 0 as my terminal point. Now it says assume you have a different vector, negative 6i plus 2j minus 3k. Find the unit vector in the direction of v. So unit vector again is, I have my negative 6 to negative 3, but I need my length. It's the square root of negative 6 squared plus 2 squared plus negative 3 squared. That's the square root of 36 plus 4 plus 9, which is the square root of 49. That's nice. So I need to take all of my terms and divide them by 7. And this is the unit vector in the direction of v. I don't really know why I grouped those two problems together when they have very little to do with each other, but it's just an application. Number 6, we skipped last year because kids were scared of it, so we'll go ahead and do it again skip it this year. Don't worry so much about it, I won't put it on the test. You can work it out, and if you have questions on how to do it, you can email me and I will explain it to you. But it has to do with the weight distribution of the camera. Again, if 120 pounds of force is applied to each leg, and each leg is equal length, so therefore has the same force applied, that means 40 pounds is being applied to each leg. So it really just wants you to represent the force applied to each leg as a vector, so keep that in mind. And that's it for 11.2, but we'll roll right into 11.3. Okay, so 11.3 starts talking about things we can do with vectors. When you learn about a new type of math, whether it's like a matrix, usually there's operations you can apply to these things. Well, vectors have an operation, and the first one is the dot product. So even though we have two vectors, the dot product of two vectors yields a scalar. It's like the determinant of a matrix, or something like that. Or when you multiply like a row matrix times a column matrix and you just get a single number as an output. Okay, so the definition of a dot product. The dot product of u and v, which we call u dot v, is you multiply the components, the common components, so the first term times the first term, and then second term times second term, and you add them together to get the dot product. Similarly, for three-dimensional space, you're just multiplying three sets of things together, and you're getting an answer. So if the dot product has the following properties. If u, v, and w are vectors in the plane or in space, and let c be a scalar, The dot product is commutative. It doesn't matter which order you do it because multiplication is commutative and doesn't affect the addition between them. The distributive property, u dot v plus w, you can distribute. If you're multiplying by a scalar, the scalar distributes to only one or the other, not both. If you distributed the scalar to both, then that scalar would get squared in the next multiplication process. Because remember, u dot v is a multiplication process. So if you had 3 times, in parentheses, 2 times 5, if you distributed the 3 to both of them, it would get multiplied in twice. The dot product of 0 and anything is 0, and the dot product of any vector and itself is the magnitude of v squared. Because, again, it'll be all those terms squared, but no square root at the end. So let's just do some basics. If you use the vector 2, -2, v is 5, 8, and w is -4, 3, find the following. U dot v so you multiply the first two terms, 2 times 5 plus -2 times 8, that would be 10 minus 16, which is -6. I'm not going to do all of these, but we'll go ahead and do D as well. It says find the length of W squared, which you technically don't need to use the dot product for this. However, this is the same as W dot itself. So that would be -4, 3 times -4, 3. And of course, remember the solutions are all up in the chapter 11 notes. So you can do B and C yourself and look at what they are. So this becomes -4 times -4, which is 16. 3 times 3 is 9. So it's 25. It's just some of the things you can do with dot product. It's pretty basic arithmetic. Okay, so the dot product can also help you find the angle between two vectors. If theta is the angle between two non-zero vectors, where 0 is less than theta, which is less than pi, because pi is the greatest degree between two of them, because once you get to 180 degrees between two of them, you start shrinking the angle on the other side. Cosine theta equals u dot v over the length of u times the length of v. So it has all the possible outcomes. If cosine theta is exactly -1, then theta is pi, because what that's saying is they're going exactly opposite directions, so they're parallel but opposite directions. If the dot product is less than 0, so remember these magnitudes are always non-negative because they're squared and take the square root of them, so the only thing that determines sign is the numerator. So if the dot product is negative, then they are more than 90 degrees away, or more than pi over 2 radians apart. Closer to -1 you get, the closer to pi. Closer to 0, closer to pi over 2. If the dot product is exactly 0, they're technically considered orthogonal, which means they're at a 90-degree angle, or pi over 2 radians. If you have a positive dot product, that means they're less than 90 degrees, but greater than 0. And if they're parallel and going in the same direction, they will have exactly a 1 for cosine theta, which means the dot product, I mean, if you look at it, something dot product of itself, but that extends to parallels and multipliers as well. And speaking of what I just said, if two vectors meet at a right angle, the dot product will be 0. We refer to these as orthogonal. We don't use perpendicular because perpendicular is something we talk about generally in 3 or in 2 dimensions. And now that we're extending to possibly 3 dimensions, we are going to use the term orthogonal, even though conceptually it is very similar to perpendicular. In 3 dimensions, there can be a bunch of different things that are all orthogonal to each other. You tend to think two things that are, if two different things are perpendicular to the same line, that they should be parallel to each other. That is no longer the case in 3 dimensions. And we'll do some work with this in the next video.